All right, team, we're going to look at solving some more difficult log equations and exponential equations today. So let's just kind of start off. Let's look at this first one here. So 5 to what power is equal to 25? And this is pretty similar to what we saw the first day of equation solving, where we could actually rewrite the 25 so that the 5 and the 25 have the same base. And then this tells us that x, in fact, would have to be equal to 2. Now, this one was pretty easy to figure out. If we didn't have a nice number like this, like the 25 that we have over here, what you can do, and like an equivalent way to think about this, is to rewrite this in exponential form. So log base 5 of 25 is equal to x. Notice if we were to go back with our circular pattern, 5 to what power is equal to 25, we have a completely equivalent statement to our original problem. So then this would turn into something that you could type into your calculator. So you could do like natural log of 25 divided by natural log of 5, which, keep in mind, is equal to log of 25 divided by log of 5, which of course would be equal to 2. So we can use this kind of reasoning here to help us solve, say, 5 to what power is equal to 26. I know it has to be just slightly bigger than 2 because 26 is just ever so slightly bigger than 25. So log base 5 of 26 is equal to our exponent, our unknown value. So then we can rewrite this using our change of base formula. Again, I choose natural log just because it's 2 letters to write versus 3. And now this is something that I can type in my calculator and see what I get. I'm not able to show you guys my calculator screen while I'm typing on the iPad here, but I do want you to try typing this in with me just to make your keystrokes are correct. So you want to do natural log, or again log, of 26, and then you want to make sure you close that parenthesis, and then you can hit your division sign and then natural log of 5. And so you should get, like we thought, to about 4 decimal places here, just slightly over 2. Of course, you can check yourself and you can say, hey, is 5 raised to this power? Does that equal 26? Now, it's not going to be exactly equal to 26 because you did do some rounding here, but it's going to be really, 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 really close. So as long as you're really, really close to 26, you should be good to go. All right, so something like this, really no different here other than it's just a little bit funkier and we just have to be careful when we type this in our calculator. I cannot rewrite 5 and 200 to have the same base. So my option here is to say 5 to what power, log base 5 of 200 equals my exponent. Now, log base 5 of 200, this is just a number. This is whatever the natural log of 200 divided by the natural log of 5, whatever that equals. So again, just a number. And then I have x minus 2 on that side. So I'm going to go ahead and add 2 to both sides. And so this is my exact version of my answer. And again, I would want to try typing this in my calculator. So I would do something like natural log of 200, close that parenthesis, divided by the natural log of 5, close that parenthesis, and then I can go ahead and add 2 to it. If I do that, I get 5.292 or so. Something like this, really no different. Do notice that my base is not by itself. So I do have that 3 multiplying by my base to start with. So I do need to go ahead and divide both sides by 3 before I continue on with this problem. Now that I have that 3 taken care of and I have it simplified on the right hand side, now I can rewrite this. So this will be log base 4 of 5 is equal to x minus 1. Log base 4 of 5 is just a number. I'm going to use my change of base formula. And then notice we can go ahead and add 1 to both sides. And then whatever that is my exact answer. And the approximate answer or so, you should get just a little bit bigger than 2. Let's talk about what's happening with something like this. It's not crazy that we're adding a 9 on this side, just like the last one where we had to divide by 3. This one we're going to have to subtract the 9. But what happens here, if we try to put this in logarithmic form, we're going to have log base 5 of negative 5 equals x plus 1. This is not going to have a solution. I cannot take 5 and raise it to a power and end up with a negative number. So if you tried typing this in your calculator, if you were trying to do change of base formula on this one, you are going to get a value that does not work. So this one right here would just be the empty set, as there is no solution. If you want to think about just like a picture of what this looks like, this is an exponential graph. I guess it's shifted to the left 1 unit. And it's going to have a horizontal asymptote way up here at +9. So this graph, I don't know, it's doing something-ish like that. If that's going to be one side of my graph, and then I'm trying to set it equal to, where does this hit 4? Well, 4 is right about here. These two lines are never going to intersect each other, so this one has no solution. All right, this is going to definitely be the hardest kind of exponential equation that we're going to be solving. So just looking at what I have on both sides, we definitely did problems similar to this. However, the bases, we were able to rewrite them so that they had the same base. 3 and 6, I can't rewrite those to have the same base. I can't take 3 and raise it to some power and end up with 6. So what we can do is we're actually going to take either the log or the natural log of both sides. Again, I'm lazy. I prefer natural log because it's 2 letters versus 3. I'm going to actually take the natural log of both sides. So this gives me natural log of 3 raised to the x plus 4 power equals the natural log of 6 raised to the 2x minus 5 power. What this does now is this allows me to use the properties of logs so that I can drop these exponents out front. So I'm going to have this quantity x plus 4 times the natural log of 3 equals this quantity of 2x minus 5 times the natural log of 6. So what happens here is natural log of 3 and natural log of 6, they're just a number. And I don't know what they are. That's something I'll type into my calculator in just a second to figure out. But what I can do is distribute that coefficient, the natural log of 3, inside of these parentheses. So x times the natural log of 3 is x natural log of 3. 4 times the natural log of 3 would be 4 natural log of 3. And then we're going to distribute the natural log of 6 into the other set of parentheses. Now, if you notice, we have x's on both sides of the equation. My first step when I'm solving the equation is I do want to get the x's to be on the same side of the equation. So I'm going to go ahead and I am going to subtract x natural log of 3 from both sides. I'm just going to subtract that entire thing. And that will put my x's on the right-hand side. So then I'm going to go ahead and in the same step, I'm going to add 5 natural log of 6 to both sides. That way everything that has an x is on one side, and everything that doesn't have an x is going to be on the other side. So then I end up with something that looks like this. So again, this makes me happy because my x's are isolated and on the same side. I could maybe try to do some properties here, but I'm not really going to even worry about it too much. I don't know if it's really worth my time and effort. These would certainly be a calculator problem, which we'll get something that looks kind of ugly in the end, but we'll just be typing that into our calculator to help us figure out what it's going to be. So our trick for this next step is if we have these two x's right here, natural log of 6 and natural log of 3 are not the same. Like I need to get my x's together. What I can do is I can factor out that GCF of x. So then I still have whatever on the left-hand side. Now, if this is x times some number, I can go ahead and divide both sides by this 2 natural log of 6 minus the natural log of 3. Again, you're welcome to do some log properties on this. I tend not to, just because I'm comfortable with typing these into my calculator. And so this right here would be my exact answer. Now this is definitely a doozy to type into the calculator. I would do the numerator first, making sure you close the parenthesis after the 3 and close the parenthesis after the 6. And then I would go ahead and hit enter, and then I would hit divided by, and then I would type this entire denominator in parentheses. So I'd have to have an open parenthesis because we need to make sure both of those components stay in the denominator. And then I'd need to close the parenthesis on the 6 and then close the parenthesis on the 3. If you do that successfully, you should get 5.3737 or so, to about 4 decimal places there. Now remember, you can always check yourself with these answers. The way I do that is I would just take 3 and I would raise it to the 5.3737 plus 4 power and see what I get. And then I would take 6 and raise it to 2 times 5.3737 power and take away 5. And I should be getting the exact same thing here. Now, there's going to be a little bit off just because I did have some rounding going on. If you actually wanted to store your exact answer down here in your calculator, you could then reference that number and then you will get exactly the same number on the left and the right hand side. All right, so let's think about working with log equations here. So if we just have our function f of x equals log of x, what values is this function defined for? So we're really asking, what is the domain of this function? Well, if this is just taking log of x right here, the smallest thing I can take the log of is a positive number. So that means I'm not going to be including 0. 0 cannot happen, and as long as it's bigger than 0. So 0 to infinity, not inclusive on 0, is just what we're going to be keeping in mind here, because we're going to be getting some extraneous solutions as we're solving some of these log equations here. All right, here's my little joke for the day. So ants on a logarithm. How amazing is that? And let's look at our first one. So we actually really enjoyed solving the log equations on our first day of equation solving because they were really, really nice. We had like the log of something equals the log of something, and we just set the somethings equal to each other. Now notice here we have 3 logarithms. 2 of them happen to be on the exact same side of the equation. So what's going to happen here is we're going to use our properties of logs, and we are going to rewrite this left-hand side using 1 logarithm. So if I have natural log of x plus the natural log of the quantity x minus 8, that addition sign right there tells me I can multiply their arguments together. And that allows me to rewrite that left-hand side using just 1 logarithm. Now I have a log set equal to a log, which is fantastic because now this turns into something that we can just take their arguments and we can set them equal to each other. So x squared minus 8x equals x minus 20. I'm left with solving this quadratic. So let's get this set equal to 0. So I'm going to subtract x over, and I'm going to add the 20 over. So I get these 2 values. So I need to multiply to 20 and add to negative 9. So that means negative 4 and negative 5 would be my values. So that tells me that my possible solutions are going to be x equals 4 and x equals 5. Now, whenever we work with solving log equations, we always have to check our solution because we need to make sure that our values are going to be defined within the domain of this function. So let's take a look. Let's start with 4. If I look here at the natural log of x, if I were to plug in 4, natural log of 4 is defined. I don't know exactly what it is without my calculator, but I know that it's a positive number, and then that's going to be just fine. So it checks out for that first piece. Now, if I move on to the second piece right here, if I were to plug in 4, 4 minus 8 is negative 4, meaning I would be taking the natural log of negative 4, which I can't do. It's not defined. So 4 gets the boot. 4 is not a solution to this. And it also, notice it doesn't check out on the second one, but as soon as I find one piece of the equation that it doesn't check out with, I know I'm done. I know that can't be a value. I'm going to run into the same issue with 5. 5 minus 8 is negative 3. Natural log of negative 3 I can't have. So 4 and 5 are technically called extraneous solutions. So this one means that this would just be the empty set, or that it has no solutions to it. All right, let's look at something like this. Pretty similar to the last one in the fact that we have 2 logs on the same side, but then notice that we have just a constant here on the right-hand side. So the kind of problem we would have seen that looked like this on our time before would have been just 1 log on one side equals just a constant on the right-hand side. So let's use our log properties because notice we have the same base here, base 6, whatever, that's arbitrary. So log base 6, and then if I'm adding them, I'm going to be multiplying those arguments together. That's how I can use those properties to make my life a little bit simpler on that left-hand side. So this will be log base 6 of 3x squared minus 3x, keep that guy in parentheses, equals 3. Now, the cool thing is, I have log base something equals something. Since we have this simplified, I can now rewrite this in exponential form. So then I'm really solving the equation 6 cubed equals 3x squared minus 3x. 6 cubed, I think, is 216. And so I'm left with another quadratic that I'm going to be solving. You're welcome to use quadratic formula on this. That would be just fine. You're also welcome. The 3, and the 216 all have a common factor of 3. So if you notice that, it's just going to make your life a little bit easier, because trying to factor this one, I'd have to really think about. I'd be multiplying to 3 times 216 and then adding to negative 3. That would take me a little bit of time and some scratch paper to figure out what those values are. But if I take out that GCF of 3, now I'm multiplying to negative 72, and I'm adding to negative 1. So negative 9 and positive 8 would be my factors. So this would mean that my possible solutions would be positive 9 and negative 8. So just like the last one, I do have to go back up and check. So let's check 9 first. If I were to plug 9 back in, 3 times 9 is 27. I can totally take log base 6 of 27. If I plug in positive 9 over here, 9 minus 1 is 8. So log base 6 of 8 is definitely a number as well. So 9 checks out. Now let's try negative 8. If I plug negative 8 into the first one, right away 3 times negative 8 gives me a negative number, and I can't take the log of a negative number. So negative 8 gets the boot, and then my only solution would be positive 9. We would say negative 8 is extraneous. We did all the correct work to get there. However, it doesn't actually check out when you plug it back in. It doesn't fall within the domain of the log function there. All right, just the last two that I kind of want you to take a look at and really compare is we'll just call it problem 1 here, and we'll call it problem 2. They have all of the exact same numbers in the problem. They're the same log base. The arguments are almost the same. If you notice in this first problem, we do have parentheses around the argument. And in the second problem, the parentheses are not there. So log base 2 is only being taken of 2x. This plus 2 is not part of it. So just kind of take a look and kind of be aware that you really do have to pay attention to what the argument of the logarithm is, just to help you decide, kind of your strategy and how to solve. So if I were to, be confronted with these two problems, I am thrilled with number 1 because I have the log with the same base 2 on both sides. And then notice I can just set my arguments equal to each other. So I can take the negative 5x plus 3, set it equal to the 2x plus 2, and then I'm left with solving this really nice looking linear equation. I'm going to add 5x to both sides, and I'm going to subtract 2 from both sides. And this is going to leave me with 1/7 for my value. Do a quick double check just to make sure that 1/7 falls within the domain of the function. So negative 5 times 1/7 is negative 5/7, and negative 5/7 plus 3 is still positive. So that side is good. And 2 times a positive number plus 2 over here on the right is still going to yield a positive number. So this one checks out. 1/7 would be my solution for the first one. For the second one, it's going to make us work just a little bit. So I have logs on both sides, but I also have this constant over here on the far right. So what I need to do is I need to get my logs to be on the same side. So that means I'm going to subtract this log base 2 of 2x from both sides, because then that would leave me with the 2 on the right, and then I can use my log properties on the left-hand side to go ahead and condense down to 1 log. So I'll just rewrite it here just so we can see everything that's happening. Cool. Okay, so on this left-hand side, if I have subtraction right here, my logs are the same base. That means I can go ahead and combine them using division. So log base 2 of negative 5x plus 3, all divided by 2x, equals 2. Now I'm just left with solving this equation. since I can't do anything else with this, it's one log, it's set equal to a constant, then I can go ahead and put it in its equivalent exponential form. So 2 to the second power is equal to my argument. And so this is the equation that I'm left with solving. Let me finish off here, off to the side here. I have x's in both the numerator and the denominator, so I need to get rid of that. So both sides I'm going to multiply by 2x, and I'm just going to be scooting over here, I guess to the left to work over here. So this would be really 4 times 2x, so that left-hand side is going to clean up to be 8x equals negative 5x plus 3. And then I'm really close here to solving it. Let's add 5x to both sides, and then let's divide by 13. So x is going to equal 3/13. So let's check and make sure this is going to be in the domain of the function. So 3 times negative, or 3/13 times a negative 5, what would that be? A negative 15/13, so just over negative 1. So a number just over negative 1 plus 3 is still positive. So this left-hand side checks out. And then 2 times a positive number is still positive. So this 3/13 is going to be within the domain of each of those log functions.